Damned if I know what happened. I pulled in collective to get light on the skids and it rolled right over. It happened so fast.
We get the word to go, so I go, right now. Pull pitch and over it goes, right roll. Blade pieces flying all over the place, transmission way out there somewhere, all over in a few seconds.
Level ground, no crosswind, piece of cake. How could it happen so fast? I can't count the takeoffs I've made, but this time, wham, roll right, and we're climbing out the left window. What happened?
Dynamic rollover. That's what happened. What we aim to do is help you understand how dynamic rollover accidents happen, why, and what you can do first to prevent it from happening, and then how to correct for rollover if you think you're getting into trouble. At the United States Army Safety Center, we're concerned about the frequency of dynamic rollover accidents. Here's why. In a 10-year period studied, there were 25 dynamic rollover accidents, 8 of them in a 13-month period, and of these, 7 were to the right on level ground. As a matter of fact, 21 of the 25 have been right rolls. Dynamic rollover happens on level, prepared, and unprepared surfaces. Nobody is immune. Not the student pilot, not the IP who's teaching him, not the pilot with 150 hours, not the pilot with 2,000 hours, not you, whatever your training or experience has been. The reason is, dynamic rollover seems to relate to your concentration on the job at hand, your degree of attention at the critical moment of liftoff, and how you handle the controls. It's a procedural problem, not an equipment design or malfunction problem. And it all goes back to the first thing you learned in basic flight training, how you get that helicopter off the ground. Because if you always follow correct procedures in accordance with the Air Crew Training Manual, you'll never have a dynamic rollover accident. That's why in the next few minutes, we'll go back over the right way to perform liftoff to hover. With the correct procedure firmly in mind, we'll show you what can happen to induce dynamic rollover in 4 basic situations. Rollovers to the right and left from level ground, and rollovers on liftoff from both right and left slopes, and show avoidance and recovery procedures. We'll touch on the various helicopter types to see what effect their flight characteristics might have on the problem of rollover. And we'll look at various prepared and unprepared surfaces and their possible contributions to rollover. Finally, we'll go back over correct liftoff procedures one more time. Although all single rotor helicopters are subject to rollover, we'll be looking at the UH-1 for convenience. We'll look at the situation along the longitudinal axis from the tail of the aircraft to keep the directions in which forces act on it clear and simple. Sensing the effects of those forces is part and parcel of correct liftoff procedure. With before takeoff check completed and aircraft clear, you verify that cyclic and pedals are in neutral position. Slowly, you increase collective with a smooth, constant, positive pressure to get the aircraft light on the skids, with main rotor thrust equaling aircraft weight, so you can check control responses during this time. You apply pedal to maintain constant heading, applying cyclic as necessary to prevent sliding as the aircraft gets light on the skids. You maintain smooth application of collective with cyclic coordination to prevent drift while maintaining vertical ascent and heading until you reach hover altitude. Smooth, well-coordinated control handling, making the aircraft do what you want it to do with absolute concentration on the task at hand during those few critical moments before and as liftoff occurs. That's what it takes, this time and every time you take off. The penalty for failing to do so could be dynamic rollover. You could be penalized for being in a rush, failing to pay attention, and for rough handling of the controls, especially the collective. To show you how quickly dynamic rollover can happen, let's watch it in animation. In a moment, we'll let the animation go through right rollover in real time. Watch closely, because it won't take long. Okay? Go. One more time. Go. Main rotor blade pieces scatter. Transmission departs the airframe, structures are damaged, and pilots are lucky to avoid serious injury when dynamic rollover takes place. As you could plainly see, rollover happens so fast you're likely to be completely surprised by it, as some rollover victims have put it. One pilot said there didn't seem to be a thing he could do about it, as the aircraft rolled to the right. What you can do about it, of course, is never let dynamic rollover get started in the first place. And you do that by following correct takeoff procedures every time. But dynamic rollovers have continued to happen. And to give you a better feeling for how and why they happen, let's slow the action down. Break the problem down into smaller pieces so we can get a grip on it. Then we'll talk about the hows and whys of rollover avoidance and recovery. With the aircraft level and controls in neutral, let's review the forces acting on the helicopter before liftoff. The force, due to gravity, always acts toward the center of the Earth, as represented by this arrow from the center of gravity. Two more arrows show the reaction forces acting upward to counter the weight of the aircraft at each skid. The thrust force of the main rotor always acts at right angles to the tip path plane. If thrust is less than the force due to weight, the aircraft remains on the ground. Increasing collective increases thrust force. When this force equals aircraft weight, the helicopter is light on the skids, ready for liftoff. The main rotor rotates counterclockwise, and a reaction force due to this torque wants to turn the nose clockwise. But applying left pedal generates tail rotor thrust in the opposite direction and is used to maintain heading. Tail rotor thrust can cause the aircraft to drift right, so left cyclic is used to change the direction of the main rotor thrust to the left by the amount needed to cancel out the drift force. When these opposing forces are equal, the aircraft remains laterally over the same point on the ground. With all forces acting on the aircraft similarly coordinated and balanced, as collective is increased, main rotor thrust exceeds weight and the aircraft lifts off. Right skid first in the UH-1, slightly nose high, so that the left skid heel is the last to lose contact as the aircraft rises. This sequence varies in other aircraft with different takeoff attitudes. All right, that's the situation in a normal takeoff executed according to correct procedure. But we're saying that dynamic rollover can happen mostly to the right and also to the left while the aircraft is sitting on a level surface. And we're saying that pilot procedure and behavior is the problem. That's with no complicating factors of crosswinds, lateral CG offsets, or slope, although all these can aggravate the problem. How come? Well, let's dig a little deeper and look at what happens when you handle the controls roughly or abruptly. Let's pick it up at the point where the aircraft is light on the skids. You've got some left lateral cyclic in, and left pedal is counteracting main rotor torque. Left lateral cyclic has done one more thing we didn't mention earlier to keep things simple, but now we've got to add it in. The direction of main rotor thrust has shifted to the right of the center of gravity, shown by this dashed line. When the aircraft is airborne, and with some left cyclic applied, its center of gravity always wants to align itself with the direction of main rotor thrust to get the aircraft back into trim. This sets up a roll moment around the CG toward the left, partly offset by right roll due to the weight of the aircraft. The result is that in hover, for example, the aircraft tends to position itself in slight left roll, or left side down. With the aircraft on the ground, none of this can happen. When left cyclic is applied, skid friction with the ground or an obstacle sets up horizontal reaction forces that prevent the skids from moving left or right. The aircraft still wants to roll left due to left cyclic, and the CG still wants to align with that thrust direction. That is, move the fuselage toward the right, but it can't because of the skid friction. This impulse toward the right generates a rightward roll moment, not around the center of gravity, but around the right skid. And it is this event that sets up the conditions for right rollover if controls are improperly applied. The distance through which this roll moment is acting, or its moment arm, can be shown by this bracket. The weight of the aircraft sets up its own leftward roll moment around the skid, and the distance through which it is acting, or moment arm, is shown by the lower bracket. This is longer than the right roll moment arm, so left roll moment, due to weight, acts as a stabilizing force, resisting right roll at this point in time. The result is nothing's happening, but the situation is about to change abruptly. To keep things simple, let's assume you leave left lateral cyclic where it is throughout the following and ignore the effects of yaw, though of course it would add to your problems. Now let's say you abruptly increase collective to get off the ground fast and rapidly apply left pedal. Two things immediately happen. Main rotor thrust increases, overcoming aircraft weight, and tail rotor thrust to the right goes up, well above the leftward force due to left lateral cyclic, which remains the same as it was. This means we've got a net force to the right, and so the power of the roll moment around the right skid increases dramatically, boosted by that large increase in thrust. That's big enough to overcome left lateral force and aircraft weight, big enough to start rolling the aircraft to the right at a high rate. We'll hold at 2 degrees so you can see what happened. For one thing, the reaction force under the left skid is gone, so the weight of the aircraft is pivoting around the right skid alone. This has moved CG over the ground rightward, toward the skid, beginning to shorten its moment arm, and so reducing its stabilizing ability. Further, you've set all that weight in motion to the right, and its momentum is going to keep it going that way until some force acts to stop it, and it will keep accelerating as long as collective keeps increasing. If you haven't recognized what's going on and started recovery procedures, considering we're only a second or less past applying collective, hard to believe as it may seem, you may already have lost control of the situation under certain critical conditions we'll talk about later. Now, let's unfreeze the action and see what happens. Let's hold again at 5 degrees. Main rotor thrust force has grown, and this adds a little to leftward force due to left lateral cyclic, which should be a stabilizing force. But rightward force due to tail rotor thrust has grown even more with left pedal application, overcoming left lateral force. The right roll moment becomes more powerful as collective increases. Meantime, CG position over the ground has continued to shift rightward, reducing the stabilizing capability of this moment arm. Once again, let's unfreeze the action. We'll hold at 8 degrees to point out that recovery action depends on using left cyclic and reducing collective to counteract right roll. But you've already used a few degrees of left cyclic, leaving a smaller margin of control available if you're going to avoid mast bumping. Furthermore, any corrective action has to have been completed from 5 to 8 degrees into the rollover for any chance of success, because it will take time to counteract the momentum of all that weight, and the aircraft is still accelerating rightward. In this case, no recovery action is taken, so let's continue. By about 15 degrees, only a couple of seconds, you're at the point of no return, the critical angle beyond which no recovery is possible, due in part because even full left cyclic can't reverse the situation. This would generate a large leftward force, but even with left pedal neutral, eliminating rightward thrust from this source, a right roll moment still exists. Decreasing collective will reduce its force, but because main rotor thrust is right of vertical, recovery is impossible and right rollover must continue. Eventually, rightward motion of the CG has brought it over the right skid. The stabilizing ability of aircraft weight acting leftward around the skid has disappeared because its moment arm has diminished to zero, while the right roll moment continues to act strongly along its moment arm. Once CG gets beyond the balance point, there's no saving it. Aircraft weight, now to the right of the skid, adds its force to the right roll moment, and rollover is inevitable. If your attention and concentration are elsewhere, and you're not handling your controls smoothly, you could wind up in a situation like this, wondering what in the world happened. Avoiding dynamic rollover requires close attention and concentration in the early seconds of the takeoff maneuver. If you're smoothly coordinating your controls, responding sensitively to the forces acting on your aircraft, the way you were taught from day one, you're not going to get into trouble. But suppose right roll gets started. How do you recover? We pick up the situation at about 5 degrees right roll, in the range where recovery action has to begin if it's going to be successful. Rightward tail rotor thrust exceeds leftward force due to left cyclic because you've coordinated left pedal with increasing collective. Then main rotor thrust exceeds aircraft weight, so there is not only a right roll moment, but it's a strong force that's tending to roll the aircraft rightward at an accelerating rate as collective increases. Now you need to counteract all these forces simultaneously to stop roll right and settle the aircraft back on the ground. You apply a large left cyclic input to increase leftward force. This shortens the arm along which right roll moment is acting. At the same time, you reduce collective to bring main rotor thrust below aircraft weight, which reduces the power of the right roll moment, while you coordinate that with reduced left pedal, which reduces tail rotor thrust rightward. Now the left roll moment due to aircraft weight works for you over its long arm, overcoming forces up and to the right. If you do all this soon enough, and remember, you've only got fractions of seconds to play with, the aircraft should settle and you can start the takeoff all over again, with better control this time. It should be obvious now that a left crosswind, CG offset to the right, or downslope to the right, are all complicating factors that aggravate the problem by reducing the critical angle at which rollover will take place. Getting back to that collective for a moment, you can't just dump it. You've got to reduce it at a rate that won't cause blade contact with the fuselage. In the UH-1, it's about 40% in 2 seconds. The longer you delay recovery action, the worse off you are. Always reduce collective as prescribed, because that buys you the most in terms of getting the aircraft back under control. You've got weight greater than thrust working for you. Unfortunately, if you let the aircraft get to and beyond the critical angle, even that won't help, because while you may be able to stop the increase in rate of right roll motion, you'll no longer be able to stop it altogether, and over it goes. Now, we've also said a helicopter can roll over to the left, but now the situation is a little more favorable, and it takes more effort to get yourself into trouble. Let's say we start with the aircraft light on the skids, with tail rotor thrust just equaling left cyclic force. Say you then inadvertently apply strong left cyclic, while failing to coordinate it properly with compensating left pedal action. Leftward force due to left cyclic now exceeds rightward force due to tail rotor thrust, meaning there is net force leftward. This sets up a left roll moment around the left skid, so the aircraft wants to roll to the left. As you now abruptly increase collective and apply left pedal, this roll moment grows in power and is acting over a very long moment arm. The weight of the aircraft is doing less good because its rightward roll moment, which should be a stabilizing force, is acting over an arm that is decreasing in length. The net result is a powerful impulse driving the aircraft to roll left. Assuming no corrective action is taken, let's see what happens. Plainly, more of the same. Due to left cyclic, main rotor blade strike occurs much earlier. Avoiding left rollover gets back to basics. Don't let it get started in the first place. Use correct takeoff procedures. But if you do experience left rollover for whatever reason, recover by reducing collective as prescribed and counter the leftward rolling force by using right cyclic. If you do this the instant you sense rollover starting, you're likely to recover. The critical angle remains the same and is affected by right crosswinds, left CG offset, and downslope left conditions. Everything we've said about dynamic rollovers from level ground applies equally well to rollovers during takeoffs from upslopes both left and right, starting at the point at which the aircraft achieves a level position, and provided there is no translational motion toward the slope. Such motion is a lot like stubbing your toe while walking or running. It complicates the problem of staying upright. Add translation to the right on top of the other forces involved in right rollover, and you've really got problems. Dynamic rollovers can happen during landings too, aggravated if you use rough control action to counter upslope rollover. Get too enthusiastic about it, and you can roll in the other direction the moment the free skid hits the ground. The other obvious complicating factor is that main rotor blade tips don't have as much terrain clearance on the upslope side, so you can get blade strike even before you've used up available cyclic control. This is particularly so in the upslope left situation, when you've already tilted the tip path plane left a few degrees. Critical angle gets severely reduced, and if you get involved in left rollover, you may not have time enough to get yourself out of it. Of course, most pilots really pay close attention when maneuvering around slopes, and that's mainly what's likely to keep you out of trouble. Now, transfer that same degree of attention and concentration to operations on level surfaces, and you've got a lot going for you. That, plus performing every single takeoff you ever make using correct procedures as you learn them in basic. Now, let's look at aircraft characteristics and what effect they might have on dynamic rollover. We've used the UH-1 for explanation purposes, so let's start there. This helicopter typically lifts off nose high, so skid toes rise first, followed by the right skid heel, and then by the left skid heel. During right rollover, the right skid heel may stay in contact, leading to pivoting in yaw about this point along with roll to the right. In left rollover, that skid heel can become the pivot point. The AH-1 Cobra has a relatively high center of gravity, and this is reduced if it is carrying stores. This aircraft lifts off nose down, right skid rising first. Skid toes are forward of the mast, so the likelihood of rollover pivoting may be reduced. In the OH-58, location of vertical center of gravity position is not usually a factor, and this aircraft has a small incidence of rollover accidents, although the two are not necessarily related. This aircraft also rises nose down. Vertical CG location is not considered a factor in the TH-55 either, in the context of dynamic rollovers. This aircraft, which rises nose down, is used extensively for pilot training. This puts the monkey on the instructor's back, of course, because while a student might readily get into rollover out of inexperience, the instructor must be constantly watchful at the instant of every liftoff, ready to take control if rollover seems likely. Knowing the full story about rollover characteristics involves not only knowing yourself and your aircraft, but about environmental factors external to the aircraft that can contribute to rollover problems. Dynamic rollover happens during takeoffs from level prepared surfaces with no local obstructions, as well as unprepared surfaces of all kinds. Although your operator's manual or checklist may not emphasize it, you need to be aware of conditions that can get you into rollover. So let's review a few of them. A level concrete surface doesn't seem to pose many problems, but check the skids out anyway, to be sure a skid isn't in a hole or a crack that could cause problems, especially if the aircraft drifts during takeoff. And look out for projecting expansion joints. Adhesive surfaces like hot asphalt can stick to skids or lower the skid into grooves that can grip the skid long enough during liftoff to initiate rollover. Watch out for grooves, gouges, or other depressions too, as well as bumps or ridges acting as possible obstacles. Perforated steel planking contains lots of steel fasteners that sometimes protrude above the surface. Hang up your skids on one of these and you're a candidate for rollover for sure. In all these cases, you want to avoid taking off from any surface that might help set up a roll rate, particularly to the right, that could result in rollover. Unprepared surfaces can produce all kinds of problems, including the effects of weather extremes. Snowy surfaces are tricky because skids can break through the surface crust to become entrapped down in the snow. Icy surfaces can be even worse, covered with cracks, pits, bumps, and ridges, all of which can cause trouble. Water frozen beneath or around the skids can trap them in a bond that grips them tightly, making rollover highly possible. Almost any kind of vegetated terrain, level or sloped, includes many possible obstacles around the landing site. Be aware of ditches or other depressions, mounds or clumps of grass or small shrubbery, rocks, branches, or roots from trees. You can spot tree stumps easily. Swampy areas provide uncertain bottom conditions, subsurface obstacles, as well as others visible on the surface, any or all of which can set up conditions for rollover at takeoff. Generally speaking, though, environmental conditions and aircraft characteristics only aggravate the conditions that lead to dynamic rollover in the first place. Let's keep firmly in mind the idea that rollover can and often does take place as aircraft take off from smooth, level, prepared surfaces with no nearby obstacles. This should tell you that the real problem starts with you, that dynamic rollover is almost entirely a procedural problem that only you can do anything about. The more experienced you are, the more it's necessary to get back to basics, to the correct takeoff procedures you learned early in your flight training. You need to discipline yourself to pay close attention to the circumstances at hand, and you need to concentrate intently on what you're doing during the instant of liftoff to hover, because the next few seconds will tell the tale. Successful takeoff or dynamic rollover. Just to refresh our memories of just what the liftoff to hover maneuver really involves, let's watch it one more time. Takeoff check completed. Aircraft cleared. Cyclic and pedals in neutral. Slowly increase collective with a smooth, constant, positive pressure, checking control responses. Apply pedal to maintain constant heading. Apply applying cyclic as necessary to prevent sliding as aircraft gets light on the skids. Maintain smooth application of collective with cyclic coordination to prevent drift, maintaining vertical ascent and heading to hover altitude. It doesn't seem like all that much, but maybe that's part of the problem. Take it for granted, fail to pay attention, concentrate at the critical moment, handle your controls abruptly, and you could be in big trouble, fast. No matter which of the aircraft we've talked about that you fly, dynamic rollover is an ever-present possibility. To help you visualize the problem of dynamic rollover, how to avoid it, and how to recover from it, we first went through the correct procedure for takeoff. With that as a foundation, we showed the forces acting on the aircraft during liftoff. First, during a normal maneuver, then during rollovers both right and left from a level surface. Then we talked about slope operations, indicating that everything is about the same as soon as the aircraft reaches a level position, and we reviewed some of the special considerations involved. Next, we looked at various aircraft types to see what effect, if any, their particular characteristics have on the rollover problem. And we reviewed the problems connected with taking off from various types of surfaces, both prepared and unprepared. We wrapped up with a review of correct takeoff procedures, because that's where rollover avoidance really begins. Dynamic rollover? It's a people problem, and you're the people involved. Follow and practice the takeoff procedures as prescribed in your air crew training manual, and you'll never roll your aircraft during liftoff. You can count on it.
Loss of tail rotor